In this problem, we're going to calculate the adiabatic flame temperature when normal butane gas is burned in pure oxygen. We're going to feed both the oxygen and butane at 25 degrees C. Reaction is at 1 bar. Now the way we do this calculation is we create a pathway so we can take advantage of the idea of state function to make the calculation easier. So the green path is drawn to represent that we don't know the exact temperature versus amount of conversion in the flame, but we know for the overall process, because it's adiabatic, there's no work done, delta H is equal to 0. What we're going to do is pick a pathway where we start with butane and oxygen. At 298, we carry out reaction, so we have heat of reaction at 298. We then take the products, which are CO2 and water, and we raise their temperature to our final temperature such that delta H change 1 plus delta H change 2 adds up to 0. And this term is going to be some summation of number of moles times the integral of the heat capacity from 298 to the final temperature. There's two terms here. I've written the general, but number of moles of CO2 times its heat capacity and number of moles of water times its heat capacity. So Cp is a function of temperature. This is important because we're going to have a very high final temperature. We have to account for the fact that the heat capacity changes with temperature. We need to first write the balanced equation. So this balanced equation means we have 1 mole of butane, 13½ mole of oxygen, 4 moles of CO2, 5 moles of water. And of course, at this final temperature here, we have 4 moles of CO2 and 5 moles of water. So first, we're going to calculate the delta H for a reaction. So delta H for reaction, this is at 298 Kelvin. It's going to be the delta H of formation of water times 5 plus the delta H of formation of CO2 times 4 minus delta H of formation of butane minus delta H of formation of oxygen. Now this is 0 because it's an element. And so we can calculate the heat of reaction. So substituting in the values from tables for heat of formation at 298 K, heat of reaction, this is in kilojoules. And then we need the heat capacity terms for CO2 and water, so we look those up. So here are heat capacities as a function of temperature from a table where these in joules per mole per Kelvin. And the temperature we substitute in here is in Kelvin. And what we need to do is multiply this by 4 and this by 5, corresponding number of moles of CO2 and water in that product that's formed, and add these terms together. So the sum number of moles times the heat capacity is equal to. So here are the terms added together. Now we want to integrate this summation from our starting temperature to our final temperature, which is our adiabatic temperature. So I've shown the integration here, and then we can substitute in the two limits. So these are each now evaluated between 298 and the final temperature. So the numbers were substituted in, and then the equation was simplified to a polynomial. Now we're almost finished. We have to go back and look at our starting. We're going to add this term plus this term, and it should add to 0 because state function, we picked a different pathway to get to the same, between the same initial and final states. So now we're going to substitute into that final relationship. So now all we have to do is simplify this equation by combining these two terms and then solving the polynomial. And we can do that in Excel solver. We get a temperature of 3,867 Kelvin. Of course, it's not accurate to this many significant figures, so around 3,600 degrees C. However, it's not clear the heat capacities are very accurate at these higher temperatures, and indeed the values reported for the adiabatic temperature for butane burned in pure oxygen are significantly lower, more like 2,800 degrees C. So this is the adiabatic flame temperature that we calculate from heat of reaction and heat capacities that are a function of temperature.